Hello my people, this is video 3 on volumes of solids of revolution. We have primarily in the first two videos been dealing with disk method, and that will be the case here in this third one as well. But when we get to the next video, and if there are any after that, I still don't know how many I'm going to do, then we'll be getting into washer method in the next one, okay? Let's go ahead and jump right in. Let's deal with a region defined as y is equal to e to the x, y is equal to 0, x is equal to 0, and x is equal to, x is equal to 1. Okay? And we're going to take that region and we're going to take it around the x-axis. Trying to figure out how we should scale this. I want to make sure that you can see it. So we'll scale it 1 unit every 3. Okay, so that's 1, that's 2, that's 3, that's 1, that's 2, that's 3. And that's because I know that E, when it hits 1, is 2.71828. So it's you know, just shy, but somewhere between 2 2/3 and 2 3/4. So let's go ahead and graph e to the x. That's the only one that's has any difficulty. And I know that at -1, e to the x is, it's roughly 1/3, so we'll fudge it right there. And at 1, it's going to be a little bit more than 2 2/3. So I have e to the x looking something like that. Okay. Let's go ahead and make it pink. Okay. And then the rest of them are just, constant equations. Y is equal to 0, as of course the x-axis. Okay. X is equal to 0, y-axis. Okay. And x is equal to 1 is going to be right over here. Okay. So we should be able to, let me see if I can make that a little bit darker or even a little bit whiter, just so it's easier to see. It's going to be this region right in here. It's not a big region. It wasn't intended to be. It doesn't really matter whether it's big or small. We can still have fun with it. And I'm going to revolve it around the x-axis. Now remember, what that means is that I'm going to have cross-sections that are perpendicular, okay, to the axis of revolution. That means that I'm going to have my differential, my width basically is going to be dx, and my limits of integration are also in terms of x. So I know already that I'm going to go 0 to 1, okay? And I know that I need r squared because basically, and let me go ahead and sort of draw, and if I extended it out, this would almost look like the end of a trumpet almost, right? If you revolved it like that. And so, but you're going to have cylinders of increasing radius. Now that radius is of course determined by my y is equal to e to the x. That is going to be my r, and therefore I have r squared dx. Okay. Now that's actually pretty easy, okay, because when I simplify that by my rules of exponents, I get e to the 2x. Now that is a u sub problem. It's a really simple u sub problem because your u is 2x, and therefore your du is 2dx. It's one of those u sub problems that after you've done it a couple hundred times, you might not even bother doing it. But basically that becomes that, so that it winds up being e to the u du. But you know that basically this is going to integrate into e to the 2 to the x, right? So let's go ahead and do that. I know that as it integrates, and let's sort of block that off, as we integrate, we're going to get e to the 2x from 0 to 1. Well, finally, the 0 is not going to be incidental, right? Yay! Pi over 2, and when I plug in 1, I'm going to get e squared, and when I plug in 0, I'm going to get e to the 0. And that basically winds up being pi over 2, and e to the squared, e squared is somewhere around 7.2. Not that it matters. We're going to go ahead and plug it into our calculator and get a decimal approximation anyway, because that's pretty much, I'd like to leave it in terms of the exact value when the exact value communicates the value just fine. Unfortunately, sometimes you have something like this, and it actually takes a bit of thought to figure out, to estimate what the value is, and sometimes it's just easier to go ahead and get a decimal approximation so that I actually know what the magnitude of my answer is. And in this case, it's 10.36. Okay. Now, let's go ahead and do, let's do one or two around the y-axis. That's probably something that we're going to need a little bit more practice on. So let's go ahead and do another one with e to the x. I think that that's going to be helpful. So we have y is equal to e to the x. We have x is equal to 0. And y is equal to e. And we're going to go around the y-axis. Well, let's go ahead and set it up with the same sort of scaling that we had on the last one. I know that my e to the x is going to be roughly, at -1, it's going to be roughly 1/3 because e is 2.7, yada, yada, yada. And 1 over 2.7 is, especially if your scaling is smaller than this, is almost indistinguishable from 1/3 on the graph. I do, however, want to be careful that I get my 2.7 over here at x is equal to 1 to be a little bit more accurate, okay? Okay. There's my e to the x. Let's go ahead and color code. Y is equal to e to the x. X is equal to 0 is, of course, my y-axis. And y is equal to e is a constant function which runs right through there. Okay. Now, that tells me that it is this region right here that is being defined as the one I'm going to revolve around the y-axis. I know, because of that, that my cross-sections are going to be perpendicular and therefore are going to have a width, or in this case, a height, of dy. So my differential is in terms of y, and so are my limits of integration. So I'm going to be going from 1 to e. So 1 to e pi, and now I need r squared, but I need r to be in terms of y as well. Well, that just means that I need to go ahead and take y is equal to e to the x and turn it into x is equal to natural log y. And I'm going to take natural log y squared, because that's my r, dy. Okay. Now, this is, of course, not within the realm of possibilities for you to integrate, and therefore this is another one of those ones that's going to be helpful to do as a calculator problem. But it was instructive, the process of simply setting it up is instructive in terms of, the concept and all sorts of fun stuff like that. Let's go ahead and put our pi out in front, and then we'll pull up our integral. It's going to be 1. And remember, this e over here is the one without the exponent. This winds up being natural log of x, and that's going to be squared, and then I'm going to go to dx, and enter. And my answer is approximately 2.257 units cubed. Okay. I hope it's okay that we're picking up the pace just a smidge, guys. I do want to not have to post 10 videos for you because I have to do each problem at a crawl. And by the time you've gotten to the third video, you should be a little more comfortable with it, especially considering the fact that we did several problems the other day. Now, the last one that we're going to do for this particular video is going to be around the y-axis as well. I have y is equal to x cubed. I already can tell that I'm going to have to change the form of that bad boy. X is equal to 0, and y is equal to -8, and y is equal to 8. Okay, so let's go ahead and leave our scale. Actually, we can change the x scale without changing the y scale, and I think that that might actually be helpful. Let's make the x scale in terms of 3 boxes per unit. That sort of stretches it out and allows us to see the graph a little bit better. But let's do the y at -10 to 10. That means that when I'm doing y is equal to x cubed, 1, 1, and 2, 8 are on the graph. So it's of course 0, 0, and since that's an odd function, I know that it has -1, -1, and -2, -8 as well. And I'm going to sketch it kind of ish. Okay, that actually wasn't half bad. And we'll make it pink. I don't know why I pick up the pink one first. Now let's go ahead and do x is equal to 0, which we know is the y-axis. And then let's go ahead and do, we can do both of these in orange, okay? Since we're not gonna run the risk of confusing the two of them, okay? That means that I'm going to be interested in this and this, okay? And I'm going to be spinning it around the y-axis. Now, you should be thinking to yourself, well, gosh, won't symmetry help me in all of this? And indeed, it will. It can. Let's go ahead and just ignore the symmetry for now and just do it straight up. It is being revolved around the y-axis, and therefore my cross sections are going to be horizontal, perpendicular to that y-axis. My differential is going to be in terms of y, as is, right, as are my limits of integration, which are of course defined by these two lines, these two constant functions. So what I have here is -8 to 8. Well, now I need a representation of my radius in terms of y. So I need to take this y in terms of x equation up here and change the form into x in terms of y. That is my r, and therefore my r squared is simply y to the 2/3. So if I have y to the 2/3 from -8 to 8, and I integrate that, y to the 2/3 becomes y to the 5/3 over 5/3, okay, or 3/5 y to the 5/3 from -8 to 8, okay. I can take that 3/5 outside and pair it with the pi. So it is a constant after all, 3 pi over 5, and y to the 5/3 from -8 to 8. Well, that's actually not going to be too bad, because when I plug in 8, I'm being, or -8, I'm being asked to take the cube root and then raise it to the 5th. Well, the cube root of 8 is 2. The cube root of -8 is -2. 2 to the 5th is 32. -2 to the 5th is -32. So what I have here is 3 pi over 5 of 32 minus a -32, or 3 pi over 5 times 64. Now, 64 times 3 is going to be 192. 192 pi over 5, and that, or let's make sure we do the units cubed, and that should be my value. Now, you need to remember that because of the symmetry, and because, when this revolves around, it is going to look remarkably like a mirror image of this revolving around, it could have been 2 pi from 0 to 8 instead of negative 8 to 8 of y to the 2/3 dy. So you could have used your symmetry for those purposes right there. But either way, you would have gotten down here to 192 pi over 5 units cubed. All right, guys. In the next video, we're going to stop doing the ones where the region is flush against the axis of revolution. There's going to be a bit of a gap in there, and that gap is going to turn our disks into washers, and I will remind you in the next video exactly how we deal with that. Email me, message me with any questions that you might have. Bye, guys.